about history and to read a little bit about history of the things we are working in, like in our case, malaria. And particularly, malaria is a good example of rich history behind this disease. This can be clearly seen just by looking at this map that shows the cases of malaria deaths in Africa. And then, as you can imagine, this means that the history of the disease is very extensive. For instance, in some well-documented publications that appeared in Nature or National Geographic, it has been described that malaria has been the cause for the death of more than half of all humans that have lived until now. Just because malaria is such an ancient disease that has been with humans since the beginning of humanity in Africa, this is the reason for such a high mortality. Then I will talk about the past, not about the current history, but about the past. And as you know, history with capital letters is made of small stories. That's why the title has this parenthesis. And actually, this presentation has been adapted from a presentation that I was asked by my university to prepare last Christmas, when they celebrate every year the Nobel Prizes in science. And because, as you know, last year's Nobel Prize for Physiology or Medicine was for malaria, partially, then that's why I prepared this talk that is a little bit adapted for today's seminar. This Nobel Prize for Physiology or Medicine last year was given to 3 people whose work dealt with diseases transmitted by arthropods. Then Omura was working with onchocercosis, Campbell, I think it was filariasis, and Professor Yu too, she was working on malaria. And particularly for her work in discovering or rediscovering artemisinin for the treatment of malaria. Then when I read about Professor Tu's biography, I found there already some interesting stories. Like, for instance, she has been the first Chinese woman to earn a Nobel Prize. She was also the first person, the first Chinese person to win a Nobel Prize in physiology or medicine. And her work was the first Nobel Prize given to a research done in science and done 100% in China. So these are 3 important and interesting aspects of her work that I wanted to mention. Also, something interesting about Professor Tu is that she is known as the professor of 3 no's, because she has not a postgraduate degree. Although she's a professor, at the time she was studying in China, there were no postgraduate studies in China. So when she finished her pharmacology studies, she was promoted to professorship, and today her degree in China is equivalent to a full professor here, but technically she has not done a PhD. She has not been abroad, and she doesn't belong to any scientific society, which is encouraging, because I think this demonstrates that you can do good research without lobbying. If you don't belong to a society or academy, maybe you cannot do much lobbying, and this is an example that with hard work you can do very good research. And it's also remarkable that the work of Professor Tu was done during the 60s and 70s, which in China were a particularly hard time for scientists, because as intellectuals they were classified or denigrated as one of the 9 black categories in society. So it was a very hard time for Chinese scientists. Just because maybe somebody who is not from the malaria field might be looking at this seminar. Just a brief outline of the malaria life cycle, which, as you know, the pathogenic agent is a protist, unicellular organism, which is transmitted by mosquitoes. And then at the beginning of the cycle, a mosquito injects the parasite into the human, and this parasite is very fragile and it's always hiding inside some type of cell, either hepatocytes or inside the red blood cells during the blood cycle. And eventually the gametocytes form in the human and are taken up by a mosquito. And since we are talking of stories, there is a very nice story in this book by Miguel Otero Silva. He's a Venezuelan writer, which in this book he describes very nicely and very precisely at the physiological level the cycle of malaria. And for instance, there is no translation to the English, that's why you have here the original Spanish text. But it's an exquisite and very precise description of the cycle of the malaria parasite inside the mosquito, where he describes the formation of gametes, the oocyst, and finally the migration of the parasite to the salivary glands of the insect to restart the cycle. Okay, so since we are talking about history, first thing we have to look at is prehistory. Because malaria is a very, very ancient organism. Probably Plasmodium dates from the time of the dinosaurs. This has been proposed from evolutionary studies, since we know that there is avian malaria and also there is malaria in reptiles. It looks like at the time of the dinosaurs we had already this disease around. The ancient history of malaria, or at least the description of the symptoms, enlarged spleen, periodic fevers, chills, this has been described since very ancient times. For instance, in the Ebers papyrus in Egypt, also in the Ashurbanipal library in Mesopotamia, and the oldest written reference that I know of is in the Nai Qing, it's a medical text in Chinese, as far back as 2700 BC, almost 5,000 years ago. And probably before that, because, for instance, the fable of Hercules and the Hydra is suspected to talk about malaria, because it describes the Hydra as living in a place, in a swamp with stagnant waters, and it has been suggested that this fable has its origins in a description of malaria. Very prominent people have been killed by the disease, as you know. King Tutankhamun, I think through DNA analysis of his remains, it was found some Plasmodium DNA in there. And also from texts, we know, from written scriptures, we know that Alexander the Great and also Genghis Khan probably were killed, or at least severely debilitated by malaria. Also, we know that the people who constructed the Great Pyramids, they were given garlic, and in some of the Egyptian hieroglyphs, it's described that this was because garlic protects apparently against the presence of the mosquitoes. And there are also descriptions of pharaohs that were sleeping under mosquito nets. So they had already an idea that mosquitoes had something to see with this type of disease. In the classical antiquity, Hippocrates was probably the first one to give an accurate description of malaria and of the different types of the disease, and he described the quartan fevers, the benign tertian fevers, probably this was vivax malaria. And already some remedies for malaria were proposed by the Chinese, and actually the first mention of Artemisia annua, this is King Hao is the name in Chinese, was in this ancient Chinese text that incidentally it was not the description of artemisinin or of artemisia for malaria, but for female hemorrhoids. Don't ask me why female and not male hemorrhoids. This is a mystery, but that's it. And more recently, in 100 AD, Lucius Columella was probably the first who seriously suggested that mosquitoes, what he called animaculi, were related with malaria and probably were the responsible vector for the disease. So then here comes something interesting, because as you have seen already, the ancient Egyptians suspected that mosquitoes had something to see with malaria, but this knowledge or this suspicion was lost during the Middle Ages, and somehow it had to be rediscovered again. And it came a period that I say scientific voting, because it was not really based on experimentation, but on guesses of people, like Francesco Torti, who was the one who named the disease malaria, as we know. He suggested that the disease was caused simply by the air, not by any particular organism. Sometime later, Tomasi Crudeli and Klebs, this was the time, the golden age of microbiology, when the reason for every disease, tuberculosis, cholera, was attributed correctly to a bacteria. And then it was thought that every disease was probably caused by bacteria. And then Tomasi Crudeli and Klebs said that Bacillus malariae, bacteria, was the causing agent for malaria, which then can be this or anything else, because they had absolutely no evidence of what was this Bacillus malariae. And also, as the last example of how to approach the disease in an interesting way, was this person, Albert Freeman Africanus King, that again, he proposed that mosquitoes were related with the disease, but his picturesque approach was to suggest that they could cover the whole city of Washington with a wire as high as the Washington Monument to prevent mosquitoes from entering the city. Well, this is the scientific time. Finally, the scientific method appears with Alphonse Laveran, who is credited with discovering the causing agent of malaria, which is this Protis Plasmodium falciparum. Laveran was a physician who was working in Constantine in Algeria. And then at that time, most of the people who were looking at blood samples and trying to find the microbes responsible for diseases, they were looking at fixed samples, or they were looking at blood, very, very fresh blood, just after taking it from the person. And that, in one case, when fixing samples, with those microscopes, they could not see clearly any structures. And because they did not know what they were looking for, if you look at fresh blood and nothing is moving, you might overlook the parasite, especially if it's not stable. Then, on that particular day, Laveran, apparently, he did something different. He was not looking at the blood on the cover, on the microscope slide immediately, but he went to do something after taking the blood, taking a coffee or whatever. He was away from the microscope for about 20 minutes, half an hour. When he came back, he saw things moving. And the reason was that the malaria parasites, because they detected the drop in temperature, they started exflagellation. The gametocytes in there, they started exflagellation, so things were moving. And then Laveran saw that those things moving might be the reason for malaria, and then he looked more closely, and that was how he finally identified the parasites of malaria in the blood. Robert Koch, famous for his proposal of the bacteria causing tuberculosis and cholera, he rejected Laveran's claim for apparently no good reason. He said, that's nonsense, that cannot be. And Laveran, even he appended another claim to this one. This was a more wild guess, which is that malaria was transmitted by mosquitoes. Why he did that? Probably he did not have an experimental evidence for that. But if we see in context, at that time, the end of the 19th century, that was the prime time for British colonialism. And there were many British MDs in the tropics. It was a relatively well-paid job. They had lots of fun. You can see these guys here about to play cricket or whatever. There was not a lot of work, and apparently the climate was very nice. And Patrick Manson was one of these MDs that was at that time working in India. And he was the first person who linked a disease like filariasis with a mosquito vector. The concrete experiment was that he was working with filariasis patients, which have these large tumors. And he could see that in the blood they had lots of small worms. And obviously he saw that the worms were blocking the lymphatic nodules, etc. And then because mosquitoes were very abundant in that area, he guessed that mosquitoes were the ones who were taking the filarias from one patient and transmitting them somewhere else. To prove this, he locked a patient in a room and filled the room with mosquitoes, fresh mosquitoes, and then next morning he took the mosquitoes, dissected them, and indeed he found the filariasis worms in the mosquitoes. That was the proof that mosquitoes were the ones taking the parasites from people. Unfortunately, Manson was not, he was a physician, but he was not an expert in insects. And this is very clearly seen when he writes to London, desperately asking for books on mosquitoes. And the British Museum tells him, sorry, we don't have books on mosquitoes, we send you a book on cockroaches. We hope it's useful for your experiments. Obviously, it was not. There is a very rich correspondence that has been preserved of Manson with many other people, and in some of this correspondence it's very clearly seen that he is not an expert at least in arthropods transmitting diseases. He doesn't know the value of his work, and he was looking for help from prominent people in London. Anyway, his discovery in the disease of filariasis was correct, and he is acknowledged as the father of medical entomology. But his next hypothesis had a very, very big flaw, which is he guessed that the way the filariasis worms had to go back to the human was not by the bite of a mosquito, which is, as we know today, is the right thing. But it was when the mosquitoes died, the worms were in the waters, and then when people were drinking this contaminated water, they got the disease. And he had this idea fixed in his mind, and he wanted to demonstrate it no matter the cost of it. At that time, Manson had to go back to England because of bad health, I think. And then he had to find somebody else to do the experiments. And there is our friend Ronald Ross. Ross was not particularly interested in medicine. Actually, he had very bad grades at school. He was not interested in medicine at all. but his father, who was a very well-known physician, pushed him to take medicine, and finally he ended up in India. But in India, he was one of those apparently playing cricket and not showing much interest in medicine, until one day he looked under a microscope and he could see things moving, and somehow he was mesmerized by what he saw under the microscope, and he started writing a kind of poems and drawing things like very not very scientific. But Manson somehow could see those writings, and he thought that Ross was his man. And then he contacted Ross, and he sent him to India with the specific instructions that he should demonstrate that filariasis was transmitted to humans by drinking contaminated water, not to investigate any other thing. Here is when it starts a kind of fight between the British and the Italian schools about not only filariasis but malaria. And this again is very well documented. Manson wrote, the French and Italians will poo-poo it at first, but then he will take our hypothesis as the right one. But this was not so, actually. Giovanni Battista Grassi and Amico Bignami were the more prominent people from the Italian school who actually could demonstrate, and they published in 1896 the hypothesis that the bite of the mosquito transmitted malaria to humans. This can be demonstrated that they were there first, and if you look at the publications of Bignami and Grassi, they are wonderful, they are very nice, they are almost pieces of art, and here you can see that the life cycle of the malaria parasite is exquisitely described. In contrast, this is what Ross was drawing. Tell me skeptical, but I am not sure that Ross was before the Italians. Again, there is some, depending on who is writing the history, of course, if a British is writing it, you see no mention at all of Bignami and Grassi. If an Italian is writing it, they don't mention Ross or Manson. Then here I took strictly what Sonia Shah in her book Fever is mentioning. She is a journalist and she did an extensive research, and most of the opinions that you will see here are extracted from this book. So apparently Ross was trailing behind the Italians, that seems to be so. But he continued insisting that the work of Grassi and company was nothing compared with his magnificent work. That actually, whereas Grassi and Bignami were working with humans, Ross was working with birds. And you say that that's strange, why is he working with birds? And actually he is mentioning that the work on birds is more important than the work on humans. Well, here's where making friends second part. Ross described the malarious Indians with whom he was working as people full of field, really nearer to a monkey than a human. Nevertheless, this didn't prevent the Indian government from making stamps with Ross' face. He also didn't collaborate with people from outside of his field. That was probably the main difference between the Italian school. The Italians collaborated with entomologists, there were physicians, there were also people who work in the field desiccating areas. They talk with the people living in malarious areas. The British apparently they didn't do that, and they were not very nice to people or to their colleagues. Naturalists were just people making pretty pictures and belonging to societies. Also, even the mosquitoes themselves, they didn't escape Ross' anger. And he said that the mosquitoes were as obstinate as mules because they were not biting when they had to. And this is all described here. It's not my opinion, just in case somebody is asking. And he even went to describe Binyami as a kind of insect, spreading his 6 legs over his own work. Very disgusting words. But the truth is that, as we have seen, Binyami and Grassi came out with the correct hypothesis, and actually they were the first ones who infected a human with the bite of a mosquito in 1898. And they also described that the species of mosquito that transmitted malaria was Anopheles and not another one. Then here were Free and Robert Koch had bad memory when already everything was known about malaria and transmission and everything. He announced it that he had discovered the malaria's mosquito vector. Obviously that was not true. But what is true and interesting is that it was not Manson, not Grassi, not Binyami, but Ronald Ross, who got finally the Nobel Prize for his work on malaria. Laveran, actually also he got the Nobel Prize 5 years later, but only for the role of protozoa in causing diseases, which is not actually his main contribution, but this is how Nobel Prizes sometimes go. Anyway, as we say, time places everybody on the right position at the end, and then Ross died a bitter man. He spent his last years with not very nice opinions from his colleagues, and he even said that the word malaria made him nearly as sick as the disease itself. And the last irony, when he was already dead, Robert Ross had a mosquito species named after him, Anopheles rossi, which was suspected not to transmit malaria during his life, Ross' life. But when he was dead, this Anopheles rossi was known to transmit malaria actually, but he didn't know because he was already dead. But then the name of this species was changed to Anopheles subpictus by Grassi. Then Ross didn't have a mosquito transmitting malaria named after him. Okay. Beginning of the 20th century, it's already a sad time for malaria. Now that we know already, imagine we knew what was the cause of malaria, we knew how it was transmitted. You say, well, now it's time to go and cure the disease. Surprisingly, then it's when malaria started being used for things that were not very ethical in the opinion of many. Here we have Julius Wagner Jaurek from Austria. He was a physician who proposed that, actually he won the Nobel Prize because he was using malaria to cure people who, for instance, had syphilis. This idea came from the observation that people who had mental diseases, from time to time, after experiencing a very severe fever, they were cured. Some of them, 1 or 2% of them were cured. And then he said, wow, look, we have malaria here, which induces very strong fevers. Why don't we give malaria to syphilitic people and see if we can cure them? And actually they did. 30% of people who anyway would die of syphilis were cured by treating them, by infecting them with malaria. 10% died of malaria, and the other 60% anyway died of syphilis, but they could cure 30% of the people. And then this so-called malariotherapy was considered for a long time as something that was ethically acceptable, because the advantage of curing people who would die of syphilis were considered more important than the risk that they would die of malaria. you might think, okay, well, this is something from the beginning of the 20th century. At that time, people didn't know exactly what was ethics, and this today cannot happen. Well, we have here this Henry Judah Heimlich. You might know him because of the Heimlich maneuver. This is when you're about to choke, and then they make you this, like, to throw out the whatever is on your throat. This is the guy himself, Heimlich, showing this with a patient. Well, Heimlich, as recently as 1997, he published a paper. The research was done in China, where they seriously proposed that malaria therapy is indicated for HIV patients. This is suspected that today in China is still being used, this malaria therapy, to cure some HIV patients. It's not known, but you see this is less than 20 years ago that this was published in a well-known journal. The 20th century, it's the age of chemistry against malaria, as we know, and Paul Ehrlich, maybe it was the first one who seriously started proposing chemicals to treat malaria. He described even a magic bullet in the form of a chemical that would kill the infected cells and not the healthy cells. This was even taken to the movies. This is not Ehrlich, but this is Edward G. Robinson. It looks very much alike. The film is terrible. Don't look at it, but it's just interesting that it was well known, this idea of the magic bullet. Ehrlich was working mainly with methylene blue, which was used in the World War I to treat soldiers with malaria. Because Ehrlich, he was a staining, he was a physician and was developing lots of stains for cells. And then he could see that methylene blue was staining malaria parasites. And then he thought, well, if it binds to the parasite, somehow maybe it might kill the parasite, which is true. Methylene blue is a relatively good anti-malarial drug, and it was used during the war. But it was also started to be used in the Second World War, but it was discontinued because the soldiers didn't like that it turned the sclera of the eyes blue. And what they especially didn't like is that it turned the urine also blue. And they said, no way, I am not taking methylene blue, whatever you tell me. In this time of chemistry against malaria, quinine, it's one of the main drugs that we have. And as you know, quinine comes from the bark of a tree in South America. And this is, when I entered the malaria field, I thought that malaria was for ages all over the world, but actually malaria did not come to South America until the Europeans went there. It was strictly a disease from Africa and Eurasia, and the Europeans took malaria to America. And then quinine was used by the Native Americans to treat fevers in general. Actually, people trembling, not necessarily fever, but the Europeans saw that because the people who were living there were using this extract from quinine to treat trembling, they might as well use it for treating malaria. And actually, all these stains that people from South America are using to, it's thought against malaria, they were using just against bitings from mosquitoes, like onoto, etc. And then turning around quinine is how we came up with chloroquine, because quinine still today is very difficult and very expensive to synthesize. It was finally at the end of the 19th century. It could be chemically synthesized, but it's very, very expensive. And then, mainly because of World War II, that in the Pacific War, everybody was having problems with malaria there. The road to find something similar to quinine, but more easily synthesized is what finally ended up with chloroquine. But chloroquine was found after Second World War. All the time during World War II, it was used mainly quinine. That, like it happened with rubber, if you remember, the rubber trees it's also the rubber trees from South America. And then it was forbidden to take rubber or also cinchona tree seeds from South America under, or you were killed by the Brazil or Peruvian government. But finally, the British managed to smuggle some cinchona trees, seeds, and they took it to Java, and actually the Dutch started cultivating the tree in Java, and they had a monopoly on the production of quinine. That was also a reason that especially the Germans that did not have access to the quinine from the Dutch, they were very much interested in finding a substitute for quinine in the form of chloroquine. But for most of the Second World War, the main chemical against malaria was not against the parasite, but as you know, against the mosquito. It was the time of DDT. And we also have a Nobel Prize related more or less to malaria. Actually, it was to Paul Muller for describing DDT to fight arthropods. Until in 1962, the novel from Rachel Carson, Silent Spring, was published, which demonstrated that DDT had very bad effects on the environment, and it was forbidden. Here again, around World War II, we have a very dark age of malaria research, and is exemplified by the name of Klaus Schilling. He clearly went beyond the limits of ethics. If you remember, Jaureg, his work with malaria therapy was accepted because the final goal was to cure people who had syphilis. Schilling also started with Jaureg's restrictions on using only malaria therapy on people who have disease, but towards the end of his career, he really went to something completely different. When he retired, it was already the time in the 40s when the Nazis started to invade Europe. And then when he was without a job, he went to see Heinrich Himmler, the SS leader, and Himmler gave Schilling the order to go to Dachau, which was the first concentration camp, and take the prisoners there, not people who were sick, just prisoners, and in fact healthy people with malaria. That was probably the darkest age, and even Schilling himself in the Nuremberg trial, he acknowledged that he was doing those experiments on healthy people that were not volunteers. There was no written consent, nothing, and this was a very dark time. But then also the Nuremberg trial, the attorneys there who were defending or in favor of Schilling, they claimed that actually the Americans did the same, which actually, when you look a little bit more, you can see this description very nicely in this book by Karen Masterson, The Malaria Project. The Americans, apart from the Manhattan Project to develop the atomic bomb, they had another secret project, which was to develop a remedy against malaria. And for that, they also, they didn't take prisoners from concentration camps, because they did not have concentration camps, but they had prisons. And a very famous case is Stateville. This is a prison in Illinois, where people from the University of Chicago were doing exactly the same things that Schilling was doing in Dachau, which is they took prisoners and they promised him to reduce their term in prison, and they promised them medical care, which they did not have in normal situations. They had just a very basal medical care, but they promised if they joined this malaria research, they would have a doctor to take care of them at all moments, and they would see a reduction of their terms. And then not only were the Germans who were acting apparently not very ethically, but also on the other side there were this kind of activities. Then after this start, yes?
And why did they calculate them? What did they research in those prisoners?
They were trying all the different drugs that they were developing. Yes, that they needed them to.
American drugs?
Sorry?
In the American prisons also?
Yes, yes, yes. All these chemicals derived from quinine, which different versions of chloroquine and everything. They had like hundreds or thousands of different chemicals just by changing one atom. And they had to try them, and they could see that with monkeys it was not very easy, and the results were not very good, so they finally had to go to humans in this way. Then my last two slides, we go back to the shining light of UU2, whose Nobel Prize was because of the discovery of artemisinin. How was this achieved? UU2 was working at this time, the 60s, the 70s, when we had the Vietnam War. And at that time, Ho Chi Minh was very upset because he was losing the war and he had a lot of problems in Vietnam with malaria. And he went to his friend Mao and begged him to find a remedy for malaria. And then Mao launched the Project 523 in 1967, which was specifically to find a remedy for malaria. And here is where they hired UU2. At the beginning, she went to the Chinese pharmacopoeia. He took lots of plants from the Chinese pharmacopoeia and made lots of extracts, and they didn't find anything. And then she went to a very old Chinese book, like this Handy Therapies for Emergencies from 340 AD, where he found a description of the use of artemisinin to treat fevers, again, as we saw at the beginning of the talk. But here they describe very clearly that the extraction of artemisinin from Artemisia annua should not be done with hot water, or not even with warm water. It had to be done in temperate or cold water. And then when she did that with Artemisia annua, this is actually a weed that grows in the parking lots and side roads. It grows anywhere. But when they were soaking Artemisia annua in cold water is when Professor Tu could purify finally artemisinin, which, as we know today, is starting to show some cases of resistance. But anyway, that was the Nobel Prize last year. And as my last slide, I found something very tender about UU2. When her father gave her name, UU, he was inspired by a sentence in a book by Confucius, the Book of Odes, a very old ancient book, which had this sentence. And this is the word UU. And you will tell me what is the sentence saying. This sentence says, "Deer bleed UU while they are eating the wild how." The wild how is Artemisia, from where artemisinin is extracted. So the name that her father bestowed her, UU, it was taken from this sentence, which also contained the name artemisinin that gave her the Nobel Prize many years after that. I think that's a very nice ending to her story. And that's all. If you have some questions.